is Lopital's rule. Lopital's rule is a specific case when you are discussing limits. Okay, way back when, remember when we first talked about derivatives, part of the things we talked about were limits. We talked about limits. Okay, so we're going to go back to that. Well, now we're talking about limits. Okay. So if you go to page 452, on page 452, in the middle there is L'Hopital's rule, the first form. Suppose that f of a is equal to g of a is equal to 0. In other words, the limit when x goes to a, and I have g of x and f of x, okay? In this situation, when both the top and the bottom, when I go to a, end up being 0 over 0, then I can calculate this as being f prime g prime of a, actually. And so that's how I would do this. So I would take the derivative of the numerator and the derivative of the denominator, and I would go ahead and plug the a in, and I would calculate that value and say that is going to be the limit of this. Okay. So what does that all mean? So let's go ahead and look at example number 1. In example number 1, we have a situation where limit of as x goes to 0, I'm assuming 1 plus x minus 1 over, what is it, x, and x is going to 0. Okay, so if I put x to 0, on the top I get, this becomes 1, so the 1 minus 1 is 0. The bottom I get 0. So again, I get the 0 over 0 form. Okay, since I got 0 over 0, L'Hopital rule specifically states now I can take the derivative of the top, the derivative of the bottom, and then plug in x equals 0. Okay, so it's going to be limit as x goes to 0. If I take the derivative of this guy, I get 1/2, 1 plus x to the negative 1/2. The negative 1 goes away. I took the derivative of this, I get that. So when x goes to 0, I get 1 to the negative 1/2, which is basically 1. I get 1/2 over 1. So that's my answer. Okay. So this is the first form. And then what you have is called, in Theorem 5 on page 453, is called the strong form. And the strong form is when you take the derivative, you put this in there, and you still get 0 over 0. If I still get 0 over 0, L'Hopital rule says, well, I can do it again. I should be able to do it again. So I take the derivative again on both sides, and it works out. Okay. So that's example number 2. So let's see example number 2, see how that works, the strong form. So what we call the first time the first form or the weak form. Okay, this is a strong form or stronger form. Example number 2. Example number 2, we have square root of 1 plus x minus 1, is it? Minus x over 2 over x squared limit as x goes to 0. Okay, so I put the 0 in, I get 1 minus 1, which is 0. I get 0 over 0. So I have 0 over 0. We take the derivative of both sides, the top and bottom. The bottom is easy. I get 2x. The top again, this goes away, minus 1/2. Minus 1/2 comes from here because I take the derivative of this. So when I put 0 in, I get 1 to the this guy, so it just becomes 1. I get 1/2 minus 1/2, which is 0. I put 0 in here, I get 0. Again, so I get the 0 over 0, right? Well, since I got the 0 over 0, I'm going to take the derivative again. And when x goes to 0, this guy becomes 2. Take the derivative of this, I get what? This guy comes down here, negative 1 this, 1 plus x negative 3 over 2. This guy goes away. I put 0 in here. This becomes 1. So I'm going to end up with negative 1/8. Is that the answer? Yep, I see it. Okay, so I had to take the derivative of top and bottom twice, right? I started from here. I verified this was 0 over 0. Took the derivative of the top and the bottom. Verified I still got 0 over 0. So I could took the derivative again. Take the derivative over that and that. And so I end up getting. Okay. Example number 3. In example number 3, evaluate the following limits using Lopital's rule. Okay, so this works on one-sided derivative also, and then we're going to talk about that. One-sided limits, I'm sorry. So example number 3, on A, we have x, limit as x goes to 0. On the positive side, sine x over x squared. Okay, so what do I get on the top? If sine when x goes to 0, I get 0 here, right? Because sine of 0 is 0. I get 0 here, right? So I take the derivative of top and bottom. Take the derivative of this, I get cosine x. Take the derivative of this, I get 2x. Right? So what do I get here? When x goes to 0, what do I get? Cosine goes to 1. I get 1 here, and it's going to 0, right? 1 over 0, which basically is, or infinity, right? Infinity basically, right? Because this is 1, but this goes really, 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 really small. So I'm going to get infinity, but I'm coming from the positive side, which means that this is going to be positive. So I'm going to get actually positive infinity, right? So you can see that if I had went to the negative, everything would stay the same. But I'm going from the negative side, x is negative. So this becomes then a negative infinity. Can you see that? You're pushing the 0 from different sides. If you look at the graph, it's much more easier to look. If you look at the graph on page 454, figure 9.7, you can see that when x approaches from the negative side, it goes down to negative infinity, right? Goes down, right? Okay, so that's what they're talking about here. Okay. Okay, so then we have some more indeterminate forms. Okay. So let's look at those. We're going to get infinity over infinity. Infinity over infinity is another time when you can use the Lopital rule. Okay, let's do that. Example number 4. Example number 4. We have as x approaches pi over 2. We have secant x 1 plus tangent x. Okay, so secant x is 1 over cosine x. This is basically 1 over cosine x, right? So 1 over cosine x, 1 over cosine x. So when x goes to infinity, x goes to pi over 2. Pi over 2. This goes to what? This goes to 0, right? The bottom part goes to 0. Since this goes to 0, 1 over 0. So this is basically infinity on top. On the bottom, as tangent goes to tangent pi over 2 is infinity. So basically you get infinity over infinity. So this is a infinity over infinity form. So I'm going to take the derivative of both top and bottom. take the derivative of this, you get what? Secant x tan x. If I take the derivative of this, I get secant squared x. This goes away, and I just take the derivative of tan. Derivative of tangent is secant x squared. So this cancels out, and this cancels out. So basically, I have the limit as x approaches in this. I have sine x over cosine x, and over here I have 1 over cosine x multiplied half divided by cosine x. This is basically the same as x goes to sine x. So when x goes to pi over 2, sine of pi over 2 is equal to 1. So the answer is 1. Okay. That's it. Example number 2. It's the same thing. I mean, I'm going to 5, not 2. Just in 4. Example number 5. Number 5, limit x goes to infinity, natural log of x, and then I have 2. Well, natural log of x as x goes to infinity. Remember, natural log of x, the graph goes like that, goes on forever. So as this goes to infinity, the bottom, this guy, the graph looks like this, right? And it goes to infinity also. So you have infinity over infinity. And so you verify you have infinity over infinity. So let's go ahead and take the derivative of the top and bottom. As x goes to infinity, the derivative of this is 1 over x. The derivative of this is 2 times 1/2 over 1. Right? So this cancels out. This is basically limit as x approaches infinity over that. Right? Or like that, right? Divide top and bottom by square root of x. 1 over, this goes to infinity. 1 over infinity, 0. Okay, so that looks like that. 2 more to go. Let's do 2 more, and then we'll call it for the first half. Okay? Example number 6. Example number 6, we're going to do something that's a little different. Example number 6, we have we've done this before. Now remember we had this and we weren't really sure what to do. So what we did was we called h is equal to 1 over x. We look at it this way. If we do that, we get what? Limit, we get, this is going to be 1 over h. And this guy here is going to be sine of h. When x goes to infinity, h goes to 0. Right? So this brings us all the way back to the first semester when we looked at this. Remember looking at this? And the graph looked like that. We had the 1 here, right? So when h goes to 0, This becomes 1. And blah, 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 blah. Going to negative infinity is the same thing. I went to negative infinity here. This went to negative infinity. Okay, this will be what? Goes from, it goes to 0 now. And instead of going, it's going to go from the negative side, approaching from the negative side. It really doesn't matter which side you approach this from, right? This goes positive or negative, it doesn't matter. It still is going to be 1. If you can approach it from either side, it doesn't matter. Like that, blah, blah, blah. All right, so one more and we'll call it, take a break after that. So again, I mean, it's really just manipulating stuff, taking derivatives and making stuff. With every step that you do, you have to be able to justify why you can go and use Lopital rule. Okay, and the easiest way to say it is, well, it's a strong form, a weak form, it's a infinity over infinity, something like that. Okay. Example number 7. Okay, example number 7. We have limit when x approaches 1. One over natural log of x, 1 over x minus 1. Okay, so the book says this is infinity over infinity. I mean, says what? It's infinity minus infinity, right? Because as x approaches 1, this goes to 0, right? Natural log of the graph looks like this. 1. So as x goes to 1, this guy goes to 0, 0, close to 0, so it's 1 over 0, which becomes infinity. Okay, same thing over here. We get 1 over 0 type of thing, right? So in actuality, it's really not necessarily what they call this. If you go ahead and do the common denominator, you'll find it really is a different form that is masquerading as this. So if I do the common denominator, I'm going to get natural log of x times x minus 1 minus natural log of x. Okay. When x goes to 1, this goes to 0, this goes to 0. This goes to 0, and this goes to 0. I have 0 over 0, right? Which is basically what? The very first one that we talked about, right? 0 over 0. So it's really the 0 over 0 form, but it's kind of masquerading as this. Because once you go ahead and combine it, you see that's something else. Right? So now I have 0 over 0. So Lopital rule says I can take the derivative of the top and bottom. Take the derivative of this, I get 1 minus 1 over x. This is the product rule, so I take the derivative of this guy first, leave that, and then I keep that, take the derivative of that, which is basically 1, and this is what I'm going to get. Okay, so what do I get here? I get 0 minus 0, I get 1 over 0 again. Okay, so we're going to have to take, or are they going to go ahead and make us combine here now? Yeah, so I have to take the derivative one more time. Okay, so if I go ahead and let's go ahead and rewrite this. I'm going to multiply it by x across. So I'm going to get x minus 1 by x minus 1. I'm going to multiply this by x, so I'm going to get x minus 1. I'm going to multiply this guy by x. And that's just kind of makes things a little more easier to look at. Okay. So again, let's go ahead. I have 0 here, 0 and 0. So I'm going to 0 over 0. So I'm going to take the derivative one more time. I get 1. That's 0. I get 1. That's 0. I have to take the derivative of this. So something needs a product rule. Take the derivative of this, which is 1, and then take that y, minus leave that, and take the derivative of that. guy goes away. X goes to 1. So I have what here? I have 1 here. This goes to 0 minus 1. So I'm going to end up with 1 minus 1. 1 over 2. Okay. All right. So a little bit of work had to be done there, doing the product rule. Okay. And you get 1/2. That's it. So we'll take a break. We'll be done with part 1 there.